move on, of course, we've got one or two really exciting talks to look forward to. And Cynthia has many claims to fame. I am going to actually just read out one that the University of Cambridge has appointed her the Rothschild Distinguished Visiting Fellow for this, associated with this program. So welcome very much, Cynthia.
Thank you very much. Thank you, Chris, and all the other organizers. I'm delighted to be here. I'm going to talk about two works. First of all, there has been mention over the last 2 days of malice, of this result. Now, is there anybody in the room who, looking at this, doesn't know what the result is? Doesn't know what I'm referring to? Oh, great, because otherwise I wouldn't bother saying it, but since there's somebody who needs to know. So basically, this is a reference to a paper that talked about identifying the presence or absence, determining the presence or absence of an individual in a forensic mix. So you've got a crime scene, you've got a bunch of DNA at the crime scene, you take the DNA and you analyze allele frequency counts for SNPs, single nucleotide polymorphisms in the DNA. And you have the DNA of a suspect, and you're trying to determine, is that suspect in the forensic mix that gave rise to these allele frequency statistics? So you've got the statistics from your forensic mix, the mess at the crime scene. You've got the DNA of the individual, and they need one other thing, which is something about the population as a whole, statistics for the population as a whole, and they talked about getting that from HapMap, for example. But this has also now been extended to just thinking about genome-wide association studies, where the forensic mix is now the allele frequency statistics for your case group, and the HapMap is the allele frequency statistics for your control group, and now you have an individual and you have their DNA and you want to know, were they a member of the case group or not? Okay? So this is a technique, it's a forensic technique for finding a needle in a haystack. And okay, so I just said all that. It uses allele frequency statistics. So what fraction of the people, let's say, have a C in this position versus having a T for a case group, a control group, and the DNA of the target individual to decide whether this person is in the group. And it's a statistic that measures whether the target DNA is sort of closer to the case group or closer to the control group. That's how it works. Now, it's an attack, and it's a real attack, and as a result of this attack, the National Institutes of Health and the Wellcome Trust changed the publication policies for the statistics that were computed in these studies that they funded. So it had a real impact on how science is done, because now it's harder to get access to these statistics. Notice, by the way, that concepts such as identifiable information, re-identification, linkage, anonymity, those concepts had nothing to do with what I was talking about. And I'm just trying to make the point here, I'm echoing something that Jerry said. He said two things. He said that membership is something that needs to be protected in the cases of taxes, for example. And he said that maybe we should stop focusing on re-identification and think about attribute privacy. Okay. So here's an outline of the talk. First of all, I'm going to tell you a little bit more about this attack and sort of what has happened in this area since 2008, and just sort of reflect a little bit about what it tells us about the limits of privacy-preserving data analysis. And then I'm going to talk to you about a sort of mitigation for this attack, which is going about genome-wide association studies via differentially private reporting of statistics, but only significant statistics, or a small number of statistics of which we expect a large fraction to be significant. So it's a differentially private false discovery rate control algorithm. So the first set of results, this is joint work with Smith, Steinke, Ullman, and Vadan. We sort of abstract away the form of the data. And so what we have is we have data for n individuals, so there will be n rows in this data set. And for each of d attributes, we have a plus or a minus 1 for that individual. So it's an n by d matrix. And what gets reported is an aggregate, which maybe typically would be the average of these values. So for each column, we report the average. And that's what's going on in the Homer attack. That's what's being reported in the Homer attack. And also in follow-up work, so the Homer attack was very serious, and people from the statistics literature, I'll do the decoding now, Sankara Raman, Obozinski, Jordan, and Halperin, said, okay, we need to give people some guidance, some advice on what is it that's safe to publish, given that these attacks happen if you publish too much. So what these results sort of boil down to is the following. Given the exact aggregate statistics, so exact averages for the case group, and the data of one individual, and the mean for a large reference sample, those are the averages of the statistics for our control group, I can determine whether that individual is in the case group. That's the sort of cleaned up statement. And we call this determining whether an individual is in the case group tracing. And the attacks, after they've been sort of made a little bit more rigorous by the Sankara-Raman et al. Paper, show that it's enough to have a number of attributes that is on the order of the number of people in the data set. You can launch the attack with n attributes, but you're reporting exact statistics. And the size of the reference group also needed to be about n. And of course, what the reference group is doing is it's telling you about the population as a whole, so it's saying you need a pretty good estimate for the population as a whole in order to carry out this attack. Now, recently, in the paper I mentioned, we strengthened this attack. And so we're saying, well, what if you don't get the exact statistics? Maybe you had measurement error, or maybe you've deliberately perturbed the statistics for the purposes of protecting privacy. So what if we only give you now approximate aggregate statistics? And I'll tell you what kind of approximation I'm talking about in a minute. And instead of giving you an entire control group, I'm going to give you a single sample drawn from the population, a single reference sample. Then again, we can identify at least one person in the data set with high probability. And I'll talk to you in a bit about why it's just, okay, one person.
A single reference sample means one person?
Yes, the data of just one random sample from the reference population. But we also need about n squared attributes. And one more thing, and the last thing is, we're going to need that the population is not, we need some kind of an assumption about the population, that the population itself is drawn from a distribution on populations. And this is a technical point, but now that we have freed our algorithm from simply reporting the average of the values that it sees, and we let it do anything that maybe is reasonably accurate, if the algorithm knew the underlying population statistics, it could ignore the data and just report the underlying population statistics, never looking at its data, and then you could never trace. So it's a technical point that comes, it's an important point, and it comes up because we're giving the algorithm this freedom. Yes?
This sort of question cropped up yesterday, and I just wanted some clarification. When you say at least one person,
I will be very clear in a minute. What I'm saying is there is one person in the data set whose data we can trace. We are not guaranteeing that for every person in the data we can, and I'll tell you why also in a moment. Okay. Why just one traceable person? Okay. Now remember, my algorithm is liberated. It doesn't have to tell you just the averages of the actual data set. So what it might do is it might subsample. So instead of averaging over everybody in the data set, it first chooses in or out for each element in the data set whether it's going to be included in a little subsample. So it will select for inclusion each individual with probability tau. And now it releases the average of the selected individuals, ignoring completely the ones that it didn't select. So the error that it's going to give on the difference from the true aggregate will be on the order of 1 over square root of tau n. And the attacker's problem now is necessarily harder because the curator has all these extra options. If the curator chose, if I was in the data set, but the curator chose not to include me in the subsample, then there is literally no trace of me in what is reported. So we can't hope to trace everybody. Okay, so in order to, great, so I want to do some comparisons. Well, I'm going to look at sort of the statistics approach that I was just discussing from Sankara-Raman et al. And Homer et al. And the new work. So in the statistics approach, the accuracy has to be exact reporting. In this work, it's approximate. So what do I mean by approximate? Well, here is the technical definition of what I mean. Now, you can ignore that for as long as you want, and you can just settle on the following. I'm going to be reporting, the way I described it is, we're looking at the fraction of people, and we're giving a fractional answer. It's 1 over n times the sum of the xi's. So this is going to be a number which is between -1 and 1. So when I say I have a constant error, I mean that my fraction can be off by a constant amount, like a 5% error, a 10% error in this fraction, okay? So one way to think about what I'm saying is that for the purposes of this work, there exists, the theorem that we state is there exists a fixed constant alpha for the error in each of the columns that blah, blah, blah. The theorem is actually a little bit more relaxed than that. And if you like, we can go through it. It talks about errors on average, but I'd like to kind of keep it at the more intuitive level. So the size of the reference pool, traditionally n, in our work, just 1. Now you might say, why would you care about proving anything about a single reference sample? And that's a great question. And the answer is that when we first heard about Homer et al., we said, that's really cool, and that's an amazing attack, and we would like to be able to launch attacks like this in scenarios other than medical studies. If you're doing a medical study, you can insist on a case group, or there might be map statistics or something that can play the role of a case group. But suppose instead you have some other subpopulation, and you have a lot of information about this subpopulation, and you have and then we're not talking DNA anymore, just some other set of attributes. Remember, my attributes were just things between -1, or just -1s and 1s. So we've got this population. It has some sort of aggregate statistics, and I have an individual, and I want to know, is this individual a member of that population, that subgroup? Are they, people who are writing to, I don't know, I just stop. Okay, so I can't necessarily go out and collect a control group, but I might at least be able to get my hands on the information of one member of the subpopulation. I might be a random member of the subpopulation, for example. I might have a good friend who is, and now I'm trying to find out about somebody else. So one of the reasons we're so interested in this is to extend the attack to other domains. Okay. The dimension D, again, they need about linear, we need about quadratic. Their attack identifies everybody in the data set. We can only promise one person. However, suppose we require that the algorithm is more constrained in terms of what it's allowed to do, and what it has to do is, for each column, compute an average and then do something wild with that. So it's treating every individual sort of the same way in the data set. That's a symmetric mechanism. And then if we restrict ourselves to symmetric mechanisms, again, we can trace everyone. And finally, as I alluded to earlier, the previous work had no assumption on the distribution or the underlying population, but we need something. So formally, the way we formalize the problem, very similarly to the way Sankara-Raman et al. Do, is, well, we have the green stuff at the top. They didn't have that. But we have a distribution, which is a nicely spread out product distribution on -1, 1 to the d. We have a population, which we describe our population by choosing from among the sets of distributions. And then we have a reference sample, which is just one member drawn from the population. We have a case group, which is n samples from the population. And now we have a target individual y. Now, either y itself is a random member of the population, or y is a member of the case group. And these are the two things, the blue case and the green case, that we're trying to distinguish. Now, our algorithm M operates on the data set, and it produces an output Q. And the tracer, the adversary, gets the data of the target, it gets the data from the reference sample, and it gets the output of the algorithm, and it tries to say, was Y in the data set, means it came by this red path, or is it out of the data set? It's just a random member of the population. And the claim is that if Y is out, the tracer will say out with high probability. And otherwise, there's at least one xi, so that if Y is equal to xi, the tracer will say in with high probability. And the tracer is really easy to describe. So again, the tracer has here's the picture again. It has the data from the target, it has the data from the reference sample, and it has the output of the algorithm on the database. So it has target, reference sample, output of algorithm, and it just looks to see the difference in the correlation between the target and the output and the reference sample and the output. So it's asking, is the target much more correlated with the output than a random member from the population is? That's all it's doing. It's just checking the difference between those two inner products. And if it's large enough, then here delta is the probability of failure, meaning an erroneous answer. If it's large enough, it says in, and otherwise it says out. So it's extremely simple attack. The proof is complicated, but the attack is trivial. And I'm just going to say a little bit about the proof. If Y is out of the database, then the database is independent of Y. And whatever is produced by the algorithm is independent of Y. So Q is independent of Y. Q is also independent of Z. So what happens is we get that Y and Z, the target individual and the reference sample, are distributed as two independent samples from the distribution, even when we condition on any fixed, possibly inaccurate value or output produced by the algorithm. So the expected difference here is going to be 0. And it's a simple concentration bound because everything is independent that this holds with high probability. Now, it's much trickier argument to show completeness. That is, if Y is in the database, then we're likely, at least for one of the elements in the database, to say yes. So what we do is we show that if Y is in, then, well, with this expectation, is going to be at least D. And then we'll use a concentration of measure case to show that, concentration of measure argument to show that this is usually the case. Now, it's a non-trivial argument, and the reason is that these terms, which is what you get from here, these terms are not mutually independent because the Q's have some weird dependency on the X's. So even though the X's are independent of the J's, it's a difficult relationship to capture. However, the X's being independent from the J's is what matters. So these terms in red are mutually independent. And that turns out to be enough. And then we argue from here that there's at least one sort of heavy hitter in the data set that will contribute D over N. When D looks like N squared, this turns out to be large enough to trigger that, to cross that threshold in our algorithm. So that's a little bit of intuition about what's going on. What does it tell us about privacy? All we required here was constant accuracy. So as I want to drill in this phrase, repeat after me, the fundamental law of information recovery, that overly accurate estimates to too many statistics can be very not private, can completely destroy privacy. Now, as you know, differential privacy does have some things to say when the dimension is on the order of a little less than N squared. It has something non-trivial to say. And when the dimension looks like N, you can get by with errors that start looking like 1 over square root of N. Remember, 1 is what you get from everybody because we're doing fractional counts. So that's getting pretty good. That's getting near the sampling error. And David Heckerman, who is an MD PhD, who is a real expert in machine learning and for many years now has been developing machine learning and statistical approaches for genomics applications, including HIV vaccine design. His comment is, you've solved the problem. Now, let's put this in context. The problem he thinks, thinking about, I gave a talk recently and I was talking about this, and he said, well, you've solved the problem. From his point of view, he wants access to those allele frequency counts. And so if we have some technology that allows reasonably good approximations to these allele frequency counts to be published, he's thrilled. And he, for his work, is collecting data sets of the size of the order of 1 million. So he really has very, very large genomics databases. Okay. All right. Now, yes?
You maybe just go back to you mentioned briefly that you needed this other assumption about the population coming from this, the little green box.
Yeah, okay.
Where does that
come in? Again, if there is only, let's assume that there's only one possibility for the distribution on people, for what the population could look like. Okay? So let's say, look at the first column, and let's say there is a fixed probability P1 that you will have, that a randomly chosen person from the population has a C in that position, and that this is well known. Yeah, right, okay. So let's assume this. There exists an algorithm that has the true distribution hardwired into its code. I don't know how to find that algorithm, but it exists. So that algorithm gets to actually ignore all input data, and it will still be right. Very close to, okay?
Okay.
So in order to make the theorem true, we have to avoid that.
It's a very extreme.
There's probably ways in which it's less extreme, but once I have an extreme point in mind, I know, yeah, right. Okay.
Okay. All right, thanks.
Yes. Okay. So, oh, right. So, okay. So I'm not sure I completely believe that David is right and we can just release all of these statistics. In any case, we may have very, very, very large numbers of statistics where we're not in the nice little O of root n scenario. So what else could we do? So this is joint work with Weijie Su, who is going to start in the statistics department at Penn soon and be a colleague of Aaron's, and Li Zhang, who is at Google. Now, first I need to tell you about a very simple differentially private primitive. Because it's an algorithm that we're going to be using. I had designed this to be a follow-on to a tutorial, which Adam gave yesterday, but not everybody was at the tutorial, so it's maybe not quite fair. In this little primitive, we have a bunch of functions, G1, G2, G3, all the way up to Gm. And we are interested in knowing, for the given database X, which is largest, G1 of M, G2 of M, G3 of M, and so on, or maybe approximately largest. So here's an algorithm, a very simple primitive, for finding a G1, a GI, which is at least close to the maximum, without paying a privacy cost for every one of the Gs, for every one of those computations. Because as you know, the more things you do in a differentially private fashion, you're going to have to, in some sense, increase the errors to cope with all of the computations. So we want to make this as cheap as possible. So the technique is the following. The algorithm first computes, but does not release to the public, the true values, G1 of X, G2 of X, and so on. So what we're really interested in is the maximum of those. Then we're going to add noise to each value. But we don't have to add noise that scales to the sensitivity of that entire vector, G1 up to Gm. It's enough to add noise that looks like the maximum sensitivity of any one of those functions, G. And then we report only the argmax of the noisy values. So we're almost directly reporting the largest value, but we first added some noise, and then we report the largest noisy one. We report its index. Don't actually reveal any of the noisy values. And there, the proof of epsilon differential privacy is by straightforward case analysis. If you also want to get your hands on GI of X for the returned I that is close to the argmax, you have to ask, please give me this, and you will get it, let's say, with fresh noise. That would give you additional privacy loss, or you could make each computation epsilon over 2 differentially private with a cumulative loss of at most epsilon. And you can do this, of course, also for report noisy argmin. And there's another tool we're going to need from Adam's tutorial, which is the advanced composition bounds, which say that if you want to compute, let's say, just for simplicity, the same thing k different times, then you have to pay roughly a square root of k factor in your noise. And that's enough. Okay. Now, we're going towards differentially private false discovery rate. So, false discovery rate control. So, are there people who need a refresher on what FDR is? You all know? Okay, great. So how small is small enough for reporting something as significant? Well, you all know about standard thresholds, and you all know about Bonferroni corrections. And so the question is, what can you do other than Bonferroni correction? Now, does everybody here know the FDR, the Biniamini-Hochberg FDR algorithm? Great. Okay. So Biniamini and Hochberg had, at least from my outsider's point of view, not really knowing the statistics literature, what looks like a really brilliant insight, which is to say, instead of trying to be sure that everything you report out as statistically significant, is statistically significant, settle for a little bit less. Settle for the idea that you can report out a set of hypotheses, and you can expect that at most a certain fraction of them, say Q, will be false discoveries, but the remaining will be true discoveries. So they relaxed to a more probabilistic setting. And so they defined the false discovery rate to be the maximum of the number of false discoveries divided by the total number that are reported out, R. But they only, and they look at the expectation of this in the cases when at least one discovery is, there's at least one false discovery. So this is the false discovery rate, and the expectation is over the sampling in generating the data set. And here's their algorithm. So Q is a number between 0 and 1. We have our p-values. They're sorted. So p sub 1 with the brace is the smallest. P sub 2 is the next largest, and so on and so forth. And we define some thresholds, the alpha j's, where alpha j is j over m squeezed down by q. Remember, q is less than 1. So j over m times q. That's the jth threshold. And the algorithm is very simple. Starting up here, you look at this, and you say, is this thing less than alpha j? If so, then declare everything in here as potentially significant. Otherwise, go down to here and say, is this thing, p sub m minus 1, less than alpha sub m minus 1? If so, declare all of these as potentially significant, otherwise, and so on and so forth. Okay? Very simple algorithm. Little bit of intuition. Sorry. So this is what happens when you say, okay, here, I found this, and now I'm taking everything to the left. So a little bit of intuition is, suppose all of the m hypotheses were true nulls. Well, the p-value of a true null is uniformly distributed between 0 and 1. So in the interval between 0 and j over m times q, you would expect exactly, you're throwing m balls in, and you're looking in this interval, you would expect to have j times q p-values. Q is less than 1. If instead you actually have j of them, much more than you expected, then you can sort of think that maybe at most a q fraction of them are bad and the rest are true nulls. So that's my intuition for why it works. Now, for technical reasons, we're not going to use exactly this algorithm. We're going to look at an alternate, which maybe some of the statisticians can explain to me, is called the step-down version instead of the step-up. So instead of starting at the right and moving what I would call down to the left, you're starting at the left and moving what I would call up to the right, but it's called the step-down procedure. And maybe it's less significant, I don't know. Anyway, but other than that, it's the same. So you look at P1, the smallest, and you compare it to alpha 1. And if it's less than, alpha 1, then you just move on to the next, and so on and so forth. And again, at some point, you know, you will have, I mean, you actually reject it, meaning in statistics language, you consider it significant. Computer scientists would say if you're rejecting it, you're deciding it's not. So anyway, but you stop, and when you stop, you will have rejected or called significant everything here to the left. It would be interesting to see if you can guess why we want to do it this way, but no matter. To make this,
Fewer hypotheses.
so according to my expert, who is Wei Jiasu, you don't actually reject so much fewer. They're comparable in practice, and I think it's fascinating. I don't have an explanation.
By the way, Benjamin Hochberg assume independence of the p-values or some sort
We will talk about the independence assumptions very specifically when I get to the theorems. Yes. Okay, but this is the algorithm in any case. Now, remember I told you about we can't look at all of these p-values. There are lots of p-values. We can't compute them all in a noisy fashion and get anything reasonable. But I told you about report noisy min. You want to get the approximately smallest, and you're going to compare that to a threshold. And then the approximately next smallest, and compare that, and so on. So that's going to be the flavor of the algorithm. And in fact, just slightly differently, we're going to run report noisy min k times. And there's some details that I'll get to later. But report noisy min only k times, where k is going to be a number that we have chosen that we think is a reasonable number of total statistics to be reported out. Maybe it's 10, 15, maybe 100. But we're not going to get into trying for all m. We're going to set our sights much more narrowly. We're going to get by with less. And the reason that we think it might be it might be of interest to be able to carry out this more limited task is that often the point of doing these things is to find an avenue for follow-up research. And we don't have infinite resources. And maybe if we find 10 things to follow up, that's already very useful. 10 things of which you expect at most a third to be lousy and the rest to be good. Okay. So what do? We run report noisy min k times, giving us k noisy values, but I'm going to call them p's for now. Later we'll get into exactly what we do. And then we just run this procedure from the left, the so-called step down procedure, on that set, ignoring everything else, ignoring all of the p-values that did not get returned in these report noisy min k times. So I'm going to talk to you for the rest of this time about this algorithm, and I'm going to tell you a few things about it. So first of all, I'm going to tell you a little bit about a new property sort of the Beniamini-Hochberg original algorithm, which holds for the step down, step up, and other variants that have appeared in the literature. Then we're going to go into a detailed discussion of the private algorithm that I just showed you. And we're going to talk about how we do the p-value computations. And we're going to prove its power by tying its power to that of the non-private algorithm. We're going to have a relationship. So we're going to have the non-private algorithm, which is well established. Then we're going to make a relationship between the power of the private version and the power of the non-private one. And then same thing for the false discovery rate control. How well are we controlling the false discovery? Again, we connect the private version to the non-private one, and there are established results about the non-private one. And then finally, I'll say a little bit about a new proof of FDR control for the non-private algorithm that allows us to relax some of the independence assumptions. Okay, so the only independence assumption that we require is joint independence of the true nulls. There are no assumptions at all about the p-values of the relationship between the p-values of the false nulls and the p-values of the true nulls. So for example, the p-values of the false nulls could be sort of adversarially set to 1 minus the median of the p-values of the true nulls. But the true nulls will be IID in 0, 1.
Sorry, Cynthia.
Yeah. Yes.
The true null is a hypothesis that's rejected or accepted?
A true null is nothing is happening. Okay. Now, the algorithms have these thresholds, alpha 1, alpha 2, up to alpha m. In the Bini-Mini-Hochberg algorithm, the jth one is j over m times q. Given any set of thresholds, the Bini-Mini-Hochberg algorithm ones or other ones, given a set of thresholds, we say that an algorithm is compliant with this set of thresholds if either it rejects nothing, so it says nothing is interesting, or it rejects some number r greater than 0, and all of the rejected p-values are below the rth threshold in this set. Okay? Now, the theorem says that, assume that the test statistics corresponding to the true nulls are jointly independent. Then any algorithm that is compliant with the original Bini-Mini-Hochberg procedure and thresholds satisfies the following for a fixed constant c. Sorry. First of all, the FDR is not bounded by q, it's bounded by c times q, which is at most 3 times q, plus something that we don't like so much. However, if we just change the definition, and this again is, well, okay, we just change what we're looking at slightly, and we say we're only interested in the case where there are at least 2 false discoveries, then we get control at the level of c times q. So the way in which this differs by what I showed you in Bini-Mini-Hochberg is, remember in Bini-Mini-Hochberg, once you have this point, you're taking sort of everything below it. Whereas here there can be gaps, and all we require is that the stuff that you decree as significant should have a p-value that is less than the alpha r. But there can be gaps. Now, we should also notice that there's a paper by, okay, so the Bini-Mini-Hochberg algorithm requires independence of the true nulls and the false nulls. But then there's the Bini-Mini-Yekutieli, which has no assumptions, but the alpha j's are more stringent. And when you sort of decode this, that corresponds to having a c that looks like log m. So we're not quite as free as Bini-Mini-Yekutieli, but we have better control. Okay, so what is, in more detail, the private algorithm? I have till 2:30? Is that right? Okay. So p-values are computed by algorithms that operate on data sets in this context, right? And normally very often in differential privacy, we make something private by the addition of noise. But when you have a very, very small value and you add noise, you could completely trash the value. And that could be a problem. So when p-values can be very small, the additive noise can be very nasty. So our solution is we're going to be looking at logarithms, so we're going to be adding noise to some logarithms. But again, we need to be extremely careful. So we're going to say that our algorithm for computing a p-value is eta nu multiplicatively sensitive if for every pair of adjacent data sets, either both of these values are less than nu, or e to the minus epsilon times the value on x is at most the value on y, which itself is at least e to the eta, is at most e to the eta times the value on x. So it's pretty technical, but what it says is if you have a computation that has this property, and later I will show you that there's a really big class of natural things that has this property, then when you take the logs, the difference between the sensitivity, the additive sensitivity of phi of y and phi of x is bounded by eta, so it's enough to add noise that is scaled to eta over epsilon in the Laplace mechanism to maintain privacy on those logs. And again, the p-value computations of certain nice multiplicatively sensitive things are a rich and popular class. Okay, so now we'll look at the private algorithm in detail. We have a bunch of inputs. We have Q, which is related to our false discovery rate control desire. And we have a bunch of parameters. N is the total number of statistics that we have. K is the total number that we're ever going to report, a bound on that. And then these are related to the sensitivity and to the noise that we use for the Laplace, as are these. So we have some thresholds, alpha j prime, and we have our algorithms for computing the different p-values. Now, I'm going to bottom code the p-values. So phi sub j is just the bottom coded p-values where I've bottom coded at nu. So I'm not going to let it get so small that it gets messy. Then psi j is what happens when I take the log of this bottom coded p-value. So just to be clear, we start with these p-values. These numbers are not going to be to scale, but the ordering is going to be the same, meaningful. Then we do the bottom coding. So some of these guys that were very small get moved up, and they're stuck here at nu. And then you have the others. Then you take logs, and I did not shift to a logarithmic scale, but the relationship of which ones are bigger than which is maintained. Okay. And now we have our algorithm. So we start with, we run report noisy min on these values. We get 1. We take that out of consideration. We run report noisy min again. We get another 1. We take that out of consideration, and we're collecting them as we go along. So as we go along, I'm going to call them y1, y2, y3. That was the order in which I received them. That may not be in the sorted order of their non-noisy versions or even their noisy versions. But I get this set of noisy values. And then I just run Binyamini-Hochberg on these noisy values with whatever these thresholds are when I finally specify them. So why did I tell you, why do I have this here? I think what I'm showing you here is that things can have happened out of order. Right. So
Only for the ones that were bottom coded or in general? Yeah, in general. Okay.
this is completely in general. And my point here is that before I added noise, let's say this guy is smaller than that guy. After I add noise, the brown point and the blue point can change places because now I've added noise. So if this was the kth largest, maybe now the noisy version is the k minus 1th largest and something else is the kth largest. That's all I'm pointing out here. Okay, so again, this is the algorithm. Now, I'm going to add Laplace noise that is scaled for k-fold composition of the additive sensitivity of those logs. And so, and I'm using report noising min, and I've shown you the theorems for that, and so we have privacy. I've added enough noise to account for the k-fold iteration of report noising min. Now, the next statement starts with blah, 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 then with high probability, all of the draws from the Laplace mechanism will simultaneously have magnitude that is not too large. That's what this says. And it's just a statement about the Laplace mechanism. And I'm going to call this really messy term the slack. And from this statement, and this is just reminding you how we got there, we can show that the thing that ends up being called the jth largest in these sorted, noisy versions of the size isn't all that, the true value there isn't all that far from what gets reported here. These might not be from the same p-value, from the same hypotheses, but the p-values are close. And the proof strategy, okay, fine. With that, we can say that if we choose the thresholds to be quite a bit like the Beniamini-Hochberg thresholds, but adjusted with these, I'm in logs now because I'm working with the logs, not with the original values. Adjusted with those parameters from my definition of multiplicative sensitivity and slack, then we can make the following claim. If the non-private BHQ rejects some number k prime hypotheses, then with high probability, the private one will as well. And the key to that is by showing that when you've done this reordering that comes from the noise, things didn't stray too far from where they should be. So that tells us about power. For arguing about control, we prove this first, which is a new theorem about the original Beniamini-Hochberg algorithm. And I'll talk about that next. And from there, we will conclude, and I'll show you how in a second, that under those weird conditions that I mentioned before, and assuming that the test statistics corresponding to the true nulls are jointly independent, which is what we get to do over here now, then with high probability, the private BH will satisfy for, again, a fixed, I mean, it's exactly the same, only I've got Q primes here instead of Q, and Q prime has this form. And we're going to choose all of our various parameters so that this term is on the order of 1. And we end up with 1 plus little o of 1 times Q. And so the key is, after showing this, all we have to do is show that in the private version, we're going to be compliant with these other thresholds. Instead of j times q, the j times q prime. And then, so we relate the control of the privacy-preserving algorithm to the control of the non-private algorithm by this adjustment in q prime instead of q. And that's it. So I have 5 minutes left. And can't do that. I'll take it to tell you a little bit about why this compliance is enough to determine control. So the way we do this is we define an adversary's game by giving its moves, explaining what the payoff is, and telling you what its optimal strategy is. And then we prove that the false discovery rate is bounded by the expectation of the adversary's payoff. And then we analyze the payoff. So the game is the following. We've got a bunch of true null values that are drawn IID from a distribution that's at least stochastically larger than uniform. Then the adversary gets to choose the p-values for the false nulls. Then it gets to choose any subset of p-values to be rejected, so that everything that it selects is just satisfies the compliance condition. And its payoff is just the fraction of true nulls in this set. So the payoff ends up being maximized when the adversary chooses all of the blue points, chooses all of the blue points to have p-value of 0. And that because it retains complete flexibility for which sets to choose. And when we do that, we can then bound the false discovery rate by bounding the expectation of a certain random variable that's associated with these pink points. And that random variable turns out to be related to a specific backwards submartingale, and there are theorems about that. So in my last half a minute, we have reality and we have art. We have exact numbers and we have blurry numbers. And the question is, which one is right? So Aaron will talk to you a bit more about this on Friday. The stability of differentially private algorithms, sorry, this is an old slide which I should have put in with more explanation, preserves privacy and it prevents overfitting. And in fact, differential privacy protects against false discovery and overfitting that is due to adaptive data analysis, where your second question depends on your first question, and your 25th study on the census data set, this unchanging data set, is determined by the outcomes of the first 24 studies. And that's it.
That was wonderful, Cynthia. We have got a session at 5 where we could follow this up a bit more, but I think we could take a couple of questions.
Okay. Yeah.
Thank you for this talk. It's good to take care of medical data. In the first part of the talk, where you mentioned that you could, under certain conditions, trace one of the subjects. Have you shown whether it is possible to trace the subject with less information than the one you have used or not?
Yeah, and in fact, I was kind of surprised that I did not see my slide on that. For some reason, I must have suppressed it or accidentally deleted it. But the answer is, so what I talked about here, oh, how bizarre. Sorry. Okay, I accidentally hit it. So ignore the accuracy assumption. I was talking about an alpha that is constant in this column. Suppose we have the error be smaller. So less than 1, but at least 1 over square root of n. Then if we get a few, more reference samples, but we live with a lower dimensionality. Alpha is less than 1, alpha squared is less than 1, so alpha squared, n squared is smaller than n squared. Okay, lower dimensionality. Then we can actually, so that's the answer that you were looking for, but we also can track 1 over alpha squared people.
So those are the minimum conditions. So if people meet the conditions you are proposing, they are safe. The question that someone made to you is, what should we do to be safe? This is the...
Right, so to be safe, you should, the only thing that we know is safe are the bounds that are given to you by differential privacy. And what these results are saying is the differential privacy results are butting up against the theoretical limits. There's very, very little room in there. You know, polylogarithmic factor at most. Yeah.
All right. Final question.
Yeah, just following up on that, the probability that you're representing here, so the adversary is identifying a unit is in the study with high probability. That was your assertion. Is this intruder confidence? Is that mapping directly? So that what he was meaning? The intruder knows that they have identified.
They do not know, but if the probability of being wrong is, I'm just looking for the theorem statement. Probably not here. Okay. There was, in the number of attributes that you need for the attack, there was a term that looks like square root of log of 1 over delta. Delta is the probability of being wrong. Okay? So you will not make that 0 because then you would have the log of 1 over 0, and that's a very bad thing. But you can make that rather small if you have more attributes. Directly. I mean, there's this direct tie.
That's the objective.
No, so what I'm saying is you won't know for sure, but if I told you that, and I haven't plugged these numbers in, but suppose I told you that I have some algorithm and its chance of error, just for the hell of it, is 2 to the minus 100. How do you feel? Would you make a bet based on the outcome? Quite likely. Okay, so there's you need to choose delta so that the chance of error makes you happy enough.
So the at least one thing will obviously, how much bigger than at least one will depend on delta.
I didn't follow that. Maybe we.
I think we'll.
But talk to me after.
Okay. All right. Once again, thank you very much.